So today we're going to be talking about the Pearson sample correlation coefficient, or when people sometimes drop the Pearsons, they just call it the sample correlation coefficient. So to start off, let's define what a correlation coefficient is. A correlation coefficient is a quantitative assessment of the strength of the relationship between the x and y values in a set of x-y pairs. The Pearson sample correlation coefficient, let's say we have some list of x and y values, right? It just keeps going, right? What we're going to do is we're going to replace each x value by the corresponding z-score, right? And a z-score is found by subtracting the mean and then dividing by the standard deviation. And then let's replace each y value with its z-score. So we have basically converted every single one of these pairs into zx, zy, zx. And then let's say we plotted every single one of these. So we've got, let's say, this is our x, this is our y. Let's say this is our mean. This line here, let's say this is our y mean, right? And if we plot every single one of these according to these pairs, we'll have some numbers up here. This is just some random sample. That makes it easy to work with. And if we're trying to find the Pearson sample correlation coefficient, which is a measure of the strength of a linear relationship, that's all based on this equation, right? R, the correlation coefficient, is equal to the sum of the z-score of y times the z-score of the x value all over n minus 1. So you'll notice this sum here. What this means is you want to multiply the z-score of the y value times the z-score of the x value for every single one of these points, and then add them up, right? So if we focus on this upper half of the equation, and then we look at our plot here, we can figure out what the correlation coefficient is going to be pretty quickly. So we know that the z-score is the number of standard deviations that a number is away from the mean of a sample, right? So these points here, they're not only above the value of the y mean, but they're also above the value of the x mean. So that means that our z-score for x would be greater than 0, positive, and our x value, or our z-score for our y value, would also be greater than 0. And if you multiply a positive by a positive, you end up with a positive, right? So the sum of these points are all going to be positive. And then if you take these points down here, you're going to notice that they're below the mean for y and below the mean for x. So our z-score for x is less than 0, and our z-score for y is also less than 0. But then when you multiply a negative times a negative, you get a positive. So all of these points add up to a positive value too, right? And then when you take this large positive number and you divide it by n minus 1, n being the number of values here, you're going to end up with some positive number. And it's going to be a measure of the strength of the linear relationship, right? And if we flip-flop this, let's say points going like this, it'd be completely flipped, right? We would say that the z-score of the x would be less than 0, and the z-score of the y points would be greater than 0, right? Because it's above, but it's below this. And a negative times a positive is a negative, so we end up with a negative here. And then the same thing over here. Our z-score for our x is going to be greater than 0, our z-score for our y is going to be less than 0. Negative times a positive is a negative, right? And then what we have is a negative and a negative added up and then divided by n minus 1, so we're going to end up with some negative number. So it makes sense that the trend for a downward sloping linear function would be a negative correlation coefficient, and one that's positively sloping or has a positive trend is going to have a positive sample correlation coefficient. Alright, so now we're going to talk about some properties of R. So the first property is the value of R does not depend on the unit of measure for either variable. You'll notice that when you're trying to find the z-score for the x and the y values, it really doesn't care what unit it's in. It doesn't matter if it's inches, feet, miles, seconds. It doesn't care at all. The correlation coefficient is merely the strength of a linear relationship between two numerical values. It doesn't consider units at all. Our second property is the value of R does not depend on which of the two variables is considered x. As you'll notice in our equation, this multiplication here, it could flip. It could be either one, right? 4 times 2 is the same thing as 2 times 4, right? It doesn't matter at all. We simply choose one to be y and choose one to be x to make it easier for ourselves, but for the most part, you could switch them. If you try calculating one correlation coefficient one way and then flip the two variables, you should end up with the same correlation coefficient. The third property is the value of R is between -1 and 1, positive 1. So a value that is closer to 1 would be considered a strong positive relationship, between the x and y. It would determine that there is, in fact, a relationship between the two variables, and it is strong and positive. Something that's between 0.5 and 0.8 is moderate, right? And something that's between 0 and 0.5 is considered weak. Now, you may be thinking to yourself, what, 0.5? That seems pretty close to 1. Why is it weak? Well, there's this other thing called the coefficient of determination, and basically what it shows is the proportion of variation in observed y's that can be explained by an approximate linear relationship. And we find the coefficient of determination by squaring our R value. So if you square 0.5, you end up with 0.25. So that means that about 25% of the data can be explained by an approximate linear relationship. And 25%, I would say, is pretty bad. It's pretty weak, as one would say. And then as you're continuing down the negative side, you would see that anything between -0.5 and 0 would be considered a weak negative relationship. And anything between -0.8 and -0.5 it is a moderate negative relationship, and -1 and -0.8 is a strong negative relationship. Cool. Next we have R equals 0 or R equals 1 only when all the points in a scatter plot of a data lie exactly on a straight line that slopes upward. So you rarely would find this in a sample piece of data. It would be really freakish data for it to just have everything be linear. But the same can be said about R equals -1, right? R equals -1 is going to be only true when all the points in a scatter plot of a data lie exactly on a straight line that slopes downward. The important thing with this property, to not confuse, is that doesn't mean that the slope is 1, right? The slope can be 5, the slope 6, 7, 2, 10, I don't know, any number. It doesn't have to be 1. And then our last property, the value of R is a measure of the extent to which x and y are linearly related. Emphasis on linearly. It doesn't give us a measure of the extent to which x and y are related, period, right? Just because it has a relatively weak R value for a linear relationship doesn't mean that there isn't a quadratic relationship or any other strong relationship. So keep an open mind. If you tested it for a linear relationship, there's a possibility it still has a relationship between x and y. And that's how easy the Pearson sample correlation coefficient is. Ooh, it's the end screen. Click on one of these links to be directed to that playlist. And don't forget to subscribe!